All right, so welcome to OfficeHr4. Thank you for tuning in. As usual, I'll probably just say a few things about the upcoming exam. The window is from Wednesday morning to Monday night, and since it's a 2-hour exam, you can't start later than 10 o'clock Monday night, and you can't start before 8 a.m. Wednesday morning. However, you can work that around your schedule. But you do want to schedule the exam with ProctorU as soon as you can. And so I'm going to briefly talk about what kind of things to think about are on the exam. It's a lot of Chapter 4. About half of the exam will be on Chapter 4, particularly the last half, when we start talking about isotopes and proton number and atomic weights and electron configuration and so on, and orbitals. And then in Chapter 6, the first 6 subsections of that go through drawing Lewis structures. Okay, and so the main thing to keep in mind, since I've already done atoms in previous office hour, is that in Chapter 6, it starts off with ions and then ionic compounds and then molecules and covalent bonds that hold them together. And you really need to know instantly by looking which one you have. And so because ionic compounds, their formula is determined by the ratio of the ions so that the total charge is 0, and the naming is done just basically by the name of each ion. Covalent compounds are named completely different. Their formulas are determined by the Lewis structures that you can form with these. Okay, so just to briefly review, the most important polyatomic anions you need to know: carbonate, nitrate, phosphate, sulfate, and chlorate. And then, of course, if you apply the rules, you figure out what the ites are, which is 1 oxygen less. So chloride is ClO2 minus, sulfite is SO3 2 minus. So when you remove the oxygen to form the ites from the ates, the overall charge stays the same, so that's easy to kind of remember. And it's 1 less oxygen. If there's 2 less, it's hypoite. If it's 1 more than the 8, it's per-8. But I'm not going to ask you any questions like, okay, which particular series exists in sulfate? Well, it turns out sulfate and sulfide are really the only common ones. Whereas for chlorate, it goes from all the way from perchlorate all the way down to hypochlorite. Phosphate and phosphide are really the only common ones there. Nitrate, nitrite. Carbonate doesn't even exist as anything else. There is no carbonite. It's just science fiction. And so those are your base polyatomic ions. Your miscellaneous, you need to know hydroxide, cyanide, acetate, and ammonium. Now, all of these polyatomic anions are in the non-metal part of the periodic table, and so when you look at them, they're actually held together with covalent bonds within the polyatomic part. And so acetate, for example, if it's written as C2H3O2, all it's really telling you is how many carbons, how many hydrogens, how many oxygens, in that order. And of course, most biochemistry involves the elements carbon, hydrogen, oxygen, and nitrogen, and that's the order in which they're usually listed in formulas. So this is CHO, and there's no N, so there's no N listed. But when you look at the Lewis structure, you can see that there's a little more information. So this is CH3, so that's called a methyl group. And then you might see COO minus. And the trick is to recognize that this O is not attached to this O. This O is attached to carbon, and this O is attached to carbon. And they're done in such a way that one of the oxygens has double bond, and then the other one is single bond. But that's about all I'm going to expect you to know about organic type compounds, besides if it's small enough for you to guess what the Lewis structure is going to be. As far as covalent compounds, if you have a single atom and a bunch of others, put the single one in the middle and then all the others around. Other compounds that like to be around on the outside are hydrogen, which usually only want a single bond, and the halogens usually only want a single bond, so you usually put them on the outside. There's a few exceptions where maybe there's chlorine in the middle and chlorate, but for the most part, halogens like to be on the outside because there's only a single bond. The other thing you need to know, going back to the ionics, is that anything in column 1A of the S block likes to be a cation +1. Any in the second column, group 2A or group 2 in the S block, likes to be a +2. There's the D block, which is most of these have more than one type of cation charge possible. So that's why you have to say what the charge is in the name. And then, but there are a few which are always particular charge, such as zinc and cadmium are always +2. Then aluminum is always +3. Now, once you go past aluminum, the elements you can't remove all the electrons, but maybe you can start adding electrons so that they have 8 in the octet in the outer shell. So the halogens in group 7 gain 1 electron in ionic compounds to form the halides. Anything in column 6 gains 2, like oxide or sulfide, or telluride. That's the name of a town in Colorado. And in group 5A, the nitride and the phosphide would have a 3- and so on. All right, now I'm ready for questions. Which formulas? So, you need to know the polyatomic ions. So, for example, you need to know carbonate CO3 2-. Okay, so make some flashcards and memorize them. And so, you need to know SO4 is 2-. And so the question would be the formulas be on the exam? All right, so the polyatomic ions, there's a table in the text. You need to memorize the things that are in that table. Now, as far as this goes, for example, you could get a question, what is this? Okay, like name it. All right, and so first thing you do is you think SO4, and you think, SO4, that looks like sulfate, which is an anion, and then you suspect, well, if it's ionic and there's an anion, there must be cation. So you look at the other part, you see potassium, which is in group 1A, so potassium +1, there's 2 of them, so I have a total of 2+ and a total of 2-. This is an ionic compound, as you should suspect once you see sulfate. Okay? And so you don't need to know this formula or anything, but you need to know the SO4 is sulfate. And you need to know the charge is sulfate. And so that's the kind of thing. So you don't need to memorize necessarily that the elements in the first column are +1s, but you should, individually, but if you know the rule and why they lose 1 electron, so they can get to the previous noble gas electron configuration, then that's what you need to know. So that's why these lose 2. So if you know that, you don't need to memorize, what's the charge of magnesium? No, you just look in magnesium, it's in column 2, you think, it loses 2 electrons. All right? So there's principles to memorize or to understand. And so you'll have the periodic table, and that'll be there. These will not be given on the exam. You got to have them appear. All right. So did they clarify the question? Okay. Well, yeah. That's what I started out with. That is chapter 4, mostly starting at subsection 5, and then all the way through chapter 6, subsection 6. So 4.5 through 6.6 and omitting chapter 5. That's pretty much what it covers. And about half of each. Multiple choice. And so what I decided not to have on the exam, there will be questions and homework dealing with shapes of molecules, geometry, and polarity of the molecule as a whole, as well as polarity of individual bonds. Those questions will not be on the exam, but however, you do need to start answering questions about those. And those will be on the final. All right, any more questions? Okay. Not right now. Surely, maybe they'll start coming in again. But you know, this more or less covers, so how do you name things? So remember, this is named differently than this system. So here, I did not say di anything or for anything or whatever, all right? Sulfate, potassium. That's its name, is potassium and sulfate. And the formula only gives the ratio of ions. And so the difference between K2SO4 and then, for example, H2O is that H2O, when you look at it, you can see a little thing that has 2 hydrogens and 1 oxygen. That's called a molecule. Whereas you don't see that. All you see is, for every one of these, you see 2 of these. But how many you see, they're all just kind of here and there, here and there, here and there. And it's a very regular pattern because these are mostly solids. So molecules, 2 nonmetals bonded together with various proportions. So you can actually call this dihydrogen monoxide. And there's actually a website called dhmo.org, which talks about the dangers of dihydrogen monoxide, which sounds real dangerous, and it is dangerous, kills many people a year. And so an example of why this has to be done, named differently than these, first of all, there is no charge. These are not ionic compounds, so we can't have the proportion of oxygen and carbon determined by the charge. And so then we have to say just basically how many there is. How many carbons, how many oxygens. And we put the one to the left that's furthest away from fluorine, the one that's closest to fluorine, we put second and we call it ide instead of the element name. So this is carbon monoxide, carbon dioxide. If there was a CO3, it'd be carbon trioxide. The other thing to watch for, NO3 is a molecule. NO3 minus is a group that's covalently bonded. However, it will be found in an ionic compound because it has a negative charge. You can think of this and this being related by the fact that if you gave an electron to this, you get nitrate. This will be nitrogen trioxide. Any more questions? How many we get logged in? Oh, sure. Anything being typed in? Okay. Anyhow, there should be plenty of time to answer this, answer the questions of this exam. It's really no long and involved sorts of things. So, for example, really you're not going to be able to draw structures with Canvas test. So what I'll have is pictures of structures and ask you which one's right. The important thing about Lewis structures is even though it looks fine, it's got to be the correct number of electrons. So for example, if I draw a Lewis structure and I claim it's nitrate, it's got to have 5 valence electrons from nitrogen. It's got to have 6 times 3, 18 from the oxygen. And then 1 more from the fact that you add an electron to make it a negative overall charge. So this has to have 24 electrons. Okay. So if I show you a picture of 26, that's the first thing I would do is start counting. Any structure has 26, write out. And then start eliminating anything that doesn't have an octet rule satisfied, and hopefully what you got left is the correct answer. Okay, so those main things to look for. Correct number of electrons, and then is octet around every atom. If you can do that, you should be good. You should know your blocks of the periodic table. It's S block, D block, P block for these 6. Ah, 2 questions. Good. All right, question 1. Oh, 3. That's a great. First question. Oh, yeah. Well, you should print a periodic table. And so the Proctor U people know this. Okay, so print it. It is under Files, I believe, in the Canvas page. Print that. Yes. I do not understand that question. So the question was, if negative charge, you do what? Yep, yeah. Well, so I'm supposing the question is asking about charge. Okay, so for example, NO3 means 1 nitrogen, 3 oxygens. What does NO3 minus mean? NO3 minus means 1 N, 3 oxygens, and 1 more electron than this guy has. Okay, so if you add an electron, you increase the superscript after the whole formula by a -1. If you take away an electron, you take the superscript, and if there's a 0, of course you don't write a 0 up here. But if the number of electrons is not equal to the total number of protons in the whole thing, then you've got to write a charge, and that's always a superscript at the very end of everything. So the minus comes after all the letters and numbers, right? So OH and then just minus. CN minus. Acetate is all these atoms and then minus. Ammonium is NH4 and then just a plus sign after everything. So all of these, this says there's 1 extra electron over what chlorine atom and 3 oxygen atoms have in their valence shell. So chlorine is group 7, 7. Oxygen is group 6. There's 6 electrons from each oxygen. So that's a total of 18 plus 7 is 25. So ClO3 by itself has 25. Now if you add an electron, now you have 26. But you also have a minus charge. So that's why you got to understand how what information is being told in these formulas. Okay, subscript tells you how many, and then the superscript tells you how many extra electrons, or what the charge is from the extra electron. Remember, electrons have negative charge, so if you add 1 electron, you're actually adding a negative charge. All right, so here SO4 2 minus, however many electrons SO4 would have, you have 2 more. Phosphate, you take all the atoms from phosphorus and 4 oxygens, add them all together, and then you have 3 more electrons than that. And carbonate the same. It's critical that you get that. Okay? So that's what the superscript indicates. And that's why the Lewis structures are, for example, drawn this way. Okay, so instead of trying to say where the negative charge is, this would be perfectly fine. Okay? So you don't really try to indicate anything about where this electron is or where it even came from. All we're saying is that the whole thing overall has 1 more electron than would have been brought by all the valence electrons of every atom. Okay, and you could count them all up and see what that number should be. But whatever that number is, you should have 1 more. All right, next question. And if that student has, wants to clarify again, they can re-ask the question if that didn't answer. Well, if there's clarification, go ahead. Okay. Well, okay. So the question is, how does it affect dots on the structure? Okay? So that's really the question. Okay, you can read it and they can re-ask if it doesn't clarify. So here's the deal. You got to have this number right. This number must be right. Otherwise, you're dealing with complete garbage. All right, so how do you get that number? Every atom has an X number of valence electrons, period. Count them up. Then the superscript tells you if there's any more or any less. All right, so we will do this example, acetate. Okay? Don't look at the structure. The question is, how does this affect the dots on the structure? Well, the number of things here must equal this number we're going to get. Okay, get the number first before you even think about this. All right, so carbon, group 4, 4 electrons. Hydrogen, group 1. There's 3 of them. All right, so we've got to multiply 1 by 3. Another carbon, 4 more electrons because it's in group 4. Oxygen's group 6. This oxygen, group 6. Okay, so from the atoms, 4, 3 times 1, 4, 6, 6. Just add them all up. You get 4 and 3 and 4 and 6 and 6. It's 12, 16, 19, 23. Okay, and that's an odd number, so not likely to have that. 1 more electron. 24. All right, so the question is, how does this affect the dot structure? Well, this dot structure must have 24 electrons, period. All right, because we counted how many electrons are in the atoms and how many have been added or taken away. That number, this must have 24. All right, so let's see if I'm right. 2, 4, 6, 8, 10, 12, 14, I'm counting pairs, 16, 18, 20, 22, 24. The number is correct, okay? Any structure with 22 is the big X. All right, now the next question is, are all of the atoms' octets satisfied? So now we count by 2s around every atom. Carbon wants 8. 2, 4, 6, 8. What about this carbon? It wants 8. 2, 4, 6, 8. What about this oxygen? 2, 4, 6, 8. What about this oxygen? 2, 4, 6, 8. Okay, so you've got to learn how to count first of all, the dash is a pair of shared electrons. It's 2. This dash is 2. These double dots are 2. All right, got to learn how to count 8. Okay, and you got to know what the double dots mean, what the dash means. All right, so that's why I know this structure is correct. Okay, if, for example, I had done something different, let me draw a wrong structure with the correct number of electrons. All I did is took this structure, instead of having a double bond where these 2 electrons are shared, I have put it on the oxygen only. All right, so this has 24 electrons. The number of electrons is right, but this carbon only has 2, 4, 6 electrons. That's why this structure is wrong and this one's right. Okay? Now, if I said, okay, well, I can fix this problem with carbon by putting 2 more electrons in there. Well, now it's got 26 electrons. You can count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Wrong number of electrons, right? So both of those structures are wrong for different reasons. That's why when we're looking for the correct Lewis structure, you got to know first the number of electrons. And that's determined by the valence electrons of every atom that's in the compound. And then you have to adjust that number if it has an overall charge. Got to remember, it's kind of backwards what you might think. Adding an electron actually makes it a negative. Removing an electron makes it a positive. All right, next question. And the student can ask more questions about that if they want. Yep. Well, I mean, it doesn't matter if it's simple or complicated. I mean, you know, let me look. I doubt, Proctor, you'll be happy with that. Shoot, I didn't bring it. Print the one from the Canvas page. That's my recommendation. That's a no-brainer. You don't want to be coming to an exam and they're going to say, "Hey, that periodic table won't work right." All right? So print the one on Canvas. It's perfectly fine. It has everything you need to know. Look at it beforehand. Make sure you know what all's on it. That'll tell you what you don't want to memorize and what you do. So what's not on it, for example, is the fact that C, the element name, is carbon. That's not on the periodic table. And you're expected to know C is carbon. I don't know offhand what the one in the book looks like, but it can't have element names on it. It can't have things like S block and P block and D block and all that stuff. Can't have that either. Some versions actually exist with electron configurations. That's a big no-no, right? And so, and not only that, but looking at actual electron configurations, the rules we give you work 90% of the time. So that's why you don't want to use that. Is there another question? Sure. Yeah, sure. Okay, so with 23 electrons, we also have 23 protons here. Okay? Yes, oh yeah, that's an excellent question. So for example, CH3COO plus existed, then it would be 23 in the neutral, and then you'd subtract 1 to make a cation. So yes, so this one is 5 plus 4 times 1 is 9. And then to make the cation, you take 1 out of the 9 and you're left with 8. So this should have 8 electrons. Yes, that is exactly right. Almost all the time you're adding electrons, but the cation, yes, you would subtract 1 to get 22. Oh, well, no, that's super. That's what we want. All right? Sure. How do you figure out electron configuration? All right, so that's where I need the periodic table. This is the way I do it, okay? So, again, start with how many electrons you got. And you keep using them until you run out. It's just a different procedure. You put them in boxes. And so you got to know what order the boxes appear. And really, the periodic table's got it for you. All right? So you just go. That's why you need to know what the blocks are in the periodic table. All right, so I'm going to draw a periodic table and amaze you. I have most of the whole thing memorized. Only because I've been doing it for 50 years. Maybe not that long. All right, so we'll talk about the order from the periodic table. Let's see. All right, let me try. All right, so. All right, so that corner I'm going to leave off. Most periodic tables put hydrogen by itself. And then there's a group of 4. So. There's the D block in the middle, the transition metals. This is the S block. And then over here, the P block. So the P block is 6 wide. So 1, 2, 3, 4. Now I guess I need a little bit more room. And I'm not going to draw all the ones in the D block, but this is the way it goes. The main difficulty is knowing what the number is in front of the electrons. Okay, so we got that, and we have that, and there we go, helium. Okay, so this is the P block. So normally the order in which you fill these boxes are, every time you go to a new shell, so these form shells, shell 1, 2, 3, 4. Okay, so actually when you look at the periodic table, you should see a series of numbers at the side. It's the shell number, N. 1, 2, 3, 4, 5, 6, 7. And that's the N quantum number. And that determines more or less the major part of the energy. All right, and so we get 1s. All right, so 1s. So there's a box. All right, 1s. And then the next row, we have two types of boxes, the 2s. And then we have a set of boxes called the 2p. And every time you go up to a new row, you get a new type of box. So shell 3 has a 3s, a 3p, and a 3d. Now I'm drawing them all at the same energy, but they're not. There's an order in which you fill them. Okay, so I'm going to go ahead and draw this one up a bit. Whoops, sorry. 3s, 3p. So a p-type has 3 boxes. An s-type has 1 box, and a d-type has 5 boxes. Hopefully I can draw these. So the S-type, sorry, row 4, there's a 4s, a 4p, a 4d, and a new type called 4f. All right, so basically every time you go to a new shell, you get a new type of box. All right, so once you know this is the S block, the first electron goes into 1s. The second electron, so helium being over here would be like in the 2. The rule is you put electrons into an empty box, the lowest one's first. Okay, there's only one lowest box. The second electron has to go in with the opposite spin. You cannot have 2 ups in a box. You must have 1 up and 1 down. Now we use 2 electrons. So let's say we're trying to go way here in the periodic table, like tellurium. All right, so I've only used 2 electrons. Tellurium's got a boatload. Yeah, I don't even know. 34? Guessing. All right, so pretty sure it's 34. All right, so now we'll do the next row, starting the next, so we filled the 1s. Now we go to the next row. Row 2 has a S block, and then the P comes after it. Row 2 has 2s and 2p. Now the way you put them into a series of boxes that are all the same, like the 2p, you do up, 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 and then you start putting paired down, down, down. Okay, so I've used 10 out of the 34, so I got 24 more electrons to go. All right, so then that puts us with 10 electrons the same as neon. Okay, now I got 24 more to go. So next we go to row 3, which is starting out in the S block. That's how I know the 3s is next. And the 3p block comes next. 1, 2, 3, 4. All right, so that's 8 more. That's 18. So now we filled the p shell, the 3p, and now we have the same as argon. right, next row, what's here? Potassium and so on. So this is the 4s. Ah, look what happened. See, the shell 3 has a new type, but we're not putting electrons in yet. We're actually putting electrons into the 4s before we get to the 3d. So the way these work is, you know, row 1 is not all the one type orbital. Well, it is in row 1 and row 2. Row 2 has the 2s and the 2p being filled before anything else goes to row 3. However, for row 3, we don't fill it completely before we start on row 4. And that's why the periodic table has the order it does. So how do I know not to fill the 3d before the 4s? Because the 3d block comes after the 4s block. And then this is the 4p block, okay, which is what we got to do. All right, so put the electrons in the 4s, which I just did. Now we're going to do the D block. Well, that's going to be completely filled by 10 electrons. If you were to count these boxes, you'll see there's 10, there's 10 electrons or elements. 4, 5, 6, 8, 9, 10. So this is 3D10. There's 10 electrons in the D. Now I do 4 more to go, right? All right. So this is how they're determined. All right, so next is the 4p. And I got to do 4 electrons. Only have 4 more left. 1, second one has to go in a different box, same spin. Third one has to go here, now I have 1 more. I'll put it down. So the electron configuration is, if you were to write it down, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 4p4. All right, so let me write this down over here. 1s2, 2s2, 2p6. So this is not as informative as this. This doesn't explain why there's 6. Okay, whereas the boxes explains why there's 6. Because if you know there's only 2 in a box and there's 3 boxes, then you know why it has to be 6. And that is filled. 3s2, 3p6. What's next is 4s2, 3d10, and 4p4. And can we see that? Probably not. Okay, so this is what's called the electron configuration, is writing out this way. So we don't say square, we say 2. We just say the number. This would be 2p6. Now, so this is called orbital box diagram, right? And so we put all the electrons in here and we put all the electrons in here. Now, the next thing you can do, if you're allowed to, and if you're asked, is there a way to make this a shortcut? Okay, so if you realize this is on the 4th row, maybe I can say, okay, the first 3 rows are filled up, and why don't I just say, okay, the first 3 rows are filled up. So one way of saying that is argon. Argon is the last element on the 3rd row. So you put a square bracket, AR, and then just list what these are on the 4th row, which is 4s2, 3d10. (4p4). And that's called a shortcut. And for the orbital boxes, the shortcut would be just this part of the diagram after the 3rd row has been, or after the 3rd row in the periodic table, not the 3rd shell, 3rd row in the periodic table has been filled. So that's how you do electron configuration. Sorry, it's rather long and involved, but that's how it works. So the periodic table to me tells me what order to fill things in. I know that, you know, this is true, the 1s and then the 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, row 5. If you have shell 5, you can have up to g functions. Those never really get filled in the periodic table. we have no stable elements that go up that high. All right, so is there another question? Okay, go back and ask, just see if any of the previous questions were ignored or answered, or if somebody has a follow-up. I will say this electron configuration stuff is not going to hurt you as bad in the long run as not being able to do ionic compound formulas or names or molecule Lewis structures or names. Those are by far, when we get to further material, for example, at the end of Chapter 6, you got to know all that stuff. Whereas if you look at the end of Chapter 6, there's really nothing about electron configurations for that matter. The main thing about the electron configuration is trying to explain why 8. Why is 8 electrons special? Okay, and it's because you filled the P and the S blocks. Okay, and so there's something extra stable about that. All right, any more questions? Okay. I'm starting to think about barbecue. Okay, we'll give it another minute. Anyhow, so good luck. Keep up with your homework. It's real important. So the homework for Chapter 6 is due Wednesday night, which most of you won't be taking your exam before then, but some of you will. The workshop should have stuff with Chapter 6 as well. But try to, once you take the exam, try to make sure you're also starting Chapter 7. Chapter 7 is completely different in that it's more quantitative, more using conversion factors to say, okay, how many grams of this and how many numbers of that. But you'll see it when you get there. But it's all about conversion factors, which of course is back in Chapter 1 or 2 where we talked about those. You really need to use that routinely as a way to do conversions.